But you know something about the unit circle, I hope. Although that was a while ago, and by definition, the trig functions. By definition, you know what each of those things is, what this is and what this is, right? If it's a unit circle related to that angle, what are each of these values here? What's x and what's y?
X is sine, y is cos.
Or the other way around. Right? Okay, the x is the cosine because it's the adjacent here. Okay, x over 1, x is the cosine. Y is the sine, y over 1. If you know that, then, because if I had shown this right triangle to my grade 8, since they've done it recently, well, maybe not so recently, but at least in this year they did it, what would they write if I showed them a triangle, or what could they write? If I showed them a right, said this is a right triangle, this is x, this is y, and this is 1, what could they write about that? I'll give you a hint. Here's a hint right here. Yeah, they could write x squared plus y squared equals 1. As a matter of fact, that's the equation of a circle, and you may have learned that in grade 11. The equation of a circle is like this, x squared plus y squared equals whatever the radius is squared. But if you now know that cosine's the x value and sine is the y value, then you can replace each of these down here, right? Okay, you can replace each of these, and what could you write here that has to be true? Instead of x squared plus y squared equals 1, you could make it cos squared plus sine squared equals 1. This is the basic Pythagorean identity. Let's try. This is the basic Pythagorean identity. It's something that's always true. Whatever values you pick for x for theta here, pick any angle you want, and that will work out, right? If you take your calculator and put them in, whatever calculator you happen to have, whether it's in radians or degrees, whatever angle you pick, it should work. Okay, it should give you something. If you do sine of, I think I'm in radians here, 0.63 radians. If you square that sine ratio, and then you take the cosine ratio of 0.63 radians, and you square that ratio. Remember, you're squaring the ratio, not the angle. It should add up to 1. Any angle you pick, it's always going to be true. That's one way you could verify that this works. Another way you could verify it works is you could graph each side. You could graph 1. You could graph sine squared plus cos squared. What does that look like? 1. If I just graph y equals 1, what's it going to look like? Just a line, right? This looks like a horizontal line. If I go back now and I change this and I graph sine of x, that whole ratio squared plus cosine of that whole thing squared. If I graph it, it's going to go a lot slower. Why is it going slower this time? Yeah, it has to do some more complicated calculations or however it's programmed to do that. But it's still the same thing. It's 1 all the way across there. It's always 1 for any angle. Okay? So that's the basic Pythagorean identity. Sine squared plus cos squared equals 1. You could write it a couple different ways. Just like any other formula or anything, you can write it different ways. Like if A is B times C, you could also write it as, actually we should do something that's similar, obviously. If you have A squared plus B squared equals C squared, you could obviously write it with the A squared by itself, and it would be C squared minus B squared, and so on, right? You could put the B squared by itself, C squared minus A squared. You could do the same thing with this. You could move this over to the other side, because you should be able to recognize it either way. Or you could move this over to the other side, recognize it that way as well. So the other two forms would be something like cos squared theta equals 1 minus sine squared. Or what's the third form here? Sine squared. I guess I could put it in the nice space I actually made for it now that I look at this. What's the other way you could write it? Yeah. 1 minus cos squared. What you have to get good at recognizing is, if you see this, you have to recognize, oh, that's equal to this. You can make that change. It allows you to take something that involves two terms here and simplify it quite a bit. If you have an expression that you end up with 1 minus cos squared in it, you can change it to sine squared, and that's a lot easier to work with. It's easier to work with something with one term rather than something with two terms in it like that, a monomial instead of a binomial. There are two other Pythagorean identities that don't get used as often, but they're there if you want. They have to do with each of these things here. One of them is 1 plus tangent squared equals secant squared. The way you can show that, well, I guess I should have written it up above the proof here. If you want to prove this is an identity, and we're starting to get to in the next tutorial after this, we're getting to the idea of proving things. If you're going to prove that this is true, what you do is you take one side and algebraically try to make it look like the other side. If you're going to try and prove this, we could take this side and try and simplify it down to this, which you can do if you try changing this tangent. What could I change that tangent into? Tangent's the same as sine over cos, so tan squared is the same as sine squared over cos squared. Now if I have two terms here, 1 plus tangent, and one of them happens to be a fraction, I'm going to change the other one into a fraction as well, because then I can add them together. What fraction would I change this 1 into? Well, I want to be able to add it to this that has cosine as a denominator. If I want the denominator to be cos squared, what do I make the other side into, or the top? Because this 1 is equal to that, right? How does that help? What have I got here now?
Just sine squared.
Yeah, we got a common denominator. On top we have this. What do we have on the bottom? We have two fractions that we add together here. What did I just do?
Oh, never mind.
I added these two fractions. They have the same denominator, right? So cos squared, and the top is cos squared plus sine squared. But then here you can use this identity up above, right? If you know that this is true, you can prove that this one is true using that, right? Using that and some algebra. If you replace now this, if you see cos squared plus sine squared, what can I change that to? 1, right? That's equal to 1 over cos squared. 1 over cos squared, what's that the same as?
Secant squared.
Secant squared. Secant squared, so you got the two sides. You've shown that this side's the same as the other side. When we get to doing proofs, like you'll be able to go on to the next section and work on proofs. Proofs are just showing that the two sides are equal algebraically. That's different than what I did up above by just testing an angle. You know, we subbed in an angle and checked it or graphed it. Neither of those are proving. That's just checking if it works. But to prove it, you have to be able to work algebraically from this and show it's equal to the other side. The other Pythagorean identity is similar. It involves the other two trig functions that haven't been involved here. We had sine squared plus cos squared equals 1. If you're kind of counting, that's basic identity number 6, I suppose, and this is number 7. There's one more. It's no, that's not number 7. This is number 7. Where is it? Right here. There's number 7. There's one more that looks like this. It's 1 plus cotangent squared equals cosecant squared. You could prove that is the same as, you could prove those two sides are the same in a similar proof to this that you could try for yourself after. You have those 8 basic identities, and you're going to use them to simplify expressions. Those are all what we're going to call the basic identities. There's some other ones that we'll use elsewhere, but for the most part, those are the ones that you use most often. I am. I put that note because I kind of missed it with my other class. But so we're going to look at this simplifying expressions, and we'll go on to doing some proofs.